Okay, just now we have derived the equation of v in terms of t. So by giving you time, we may calculate the velocity, isn't it? But can we calculate velocity by giving you the displacement? How is it? What is the equation? So we may derive the second equation of velocity, which is in terms of y or displacement. Okay, how is it? Basically, the displacement equation is y equal to a sine omega t. So by rearrange the equations, you will get sine omega t equals to y over a. We just transfer a to the other side, isn't it? You will get this. And then by having square for both sides, you will get sine omega t squared equals to y squared over a squared. So this is the third equation, getting from the displacement equation. Alright, and then from the equation derived before, v in terms of t, which is v equal to a omega cos omega t. By having square for both sides, what do we get now? V squared equals to a squared omega squared cos omega t squared. And in trigo before, I think you have learned in school, sine omega t squared plus cos omega t squared equals to 1. So that cos omega t squared equals to 1 minus sine omega t squared. We just substitute into this equation. Okay, and then what do we get? Alright, so we just substitute cos omega t squared by 1 minus sine omega t squared. You will get this. So this is our fourth equation. Alright, and then we just substitute the third equation into our fourth equation, where according to the third equation, the equation is sine omega t squared equals to y squared minus x squared. Okay, sorry, this is y. This is y. Let me correct this one first. So this is y. Okay, so y. Alright, so from the third equation, which is sine omega t squared equals to y squared over a squared, we just substitute into the fourth equation here, and we just substitute sine omega t squared here with y squared over a squared, and then you will get this. Alright, so a squared, okay, we just expand the equation. So 1 minus y squared over a squared, still the same with a squared minus y squared over a squared. They are the same actually. So in this case, a squared and a squared just cancelling each other, giving you this equation. Then we just square root both sides. You will get v, and the square root of omega squared giving you omega plus minus, and the square root of a squared minus y squared. So this is the equation of velocity in terms of displacement. So by giving you the displacement, we may calculate the velocity directly. But according to this equation, we have plus minus here. So normally it's quite difficult for you to determine the direction of v. Is it to the left or to the right? Compare to the equation before, which is v in terms of t. So by substituting t into the equation, you will get v, which is positive or negative. So by getting positive means that the object is moving to the right. By getting negative, the object just moving to the left. So by using this equation, normally we just focus on magnitude only. It's quite difficult for you to identify its direction because we got plus minus here. Okay, so from the equation derived just now, we may prove that the velocity has maximum values at equilibrium, and the speed of velocity is 0 at amplitude. How is it? By using the equation before, which is v equal to plus minus omega square root of a squared minus y squared. So at the equilibrium, y equal to 0, substitute into this equation. When y equal to 0, giving you v equal to plus minus omega a. So that one is maximum velocity. Alright, and then when the particles are located at the amplitude, so the equation is v equal to plus minus omega square root of a squared minus y squared. In this case, y equals to a. Substitute into this equation. A and a cancel each other, giving you 0. So at the amplitude, v is 0. Okay, why? Because at the amplitude, the object needs to stop for a while to change its directions to be backward, isn't it? That is why the speed is 0 at that position. Alright? So this is the way how do you prove that v is maximum at the origin or equilibrium and v is 0 at the amplitude. And now let's turn to the acceleration. How do we derive the equation of acceleration for any simple harmonic motion system. Alright, so as we know, differentiation of v with respect to t giving you a. So v equals to a omega cos omega t. From this, we need to differentiate v with respect to t. Substitute into this equation. What do we get now? Okay, so we need to differentiate a omega cos omega t with respect to t. Again, a and omega just a constant. Take out this one thing. Okay, this thing first. Then we need to differentiate cos omega t with respect to t. Alright, so based on that, a omega just a constant. So we need to differentiate cos omega t with respect to t. So again, first cos omega t. We just differentiate this thing with respect to t. You will get negative sine omega t. Alright, and then again omega t with respect to t, you will get omega. So giving you a equal to negative a omega squared sine omega t. Okay, something is missing here, which is squared. It must be a omega squared. Okay, how to get that? Let me show you again lah. Okay, so a equals to d over dt of v. So v is a omega cos omega t. Alright, so in this case a omega just as constant. Take out first, and then we need to differentiate cos omega t with respect to t, giving you negative sine omega t. Alright, and then omega t with respect to t, giving you omega. Okay, so what do we have? Negative a omega omega, giving you a omega squared, and then sine omega t. So this is the equation of a. A equal to negative a omega squared sine omega t. So normally a always in negative sign. Why? Because a always towards the equilibrium, okay, or against the displacement. Alright, so this is the equation of acceleration in terms of t. Alright, and then what is the equation of acceleration in terms of displacement? Okay, so this is the equation. A equals to negative a omega squared sine omega t. As we know, according to the general equation before, okay, a sine omega t. A sine omega t representing y, isn't it? So a sine omega t equals to y. So this is y actually. So y times omega squared times negative, giving you a in terms of y. A equal to negative omega squared y. So this is the equation of acceleration in terms of displacement. So based on this equation, again, we may prove that a equals to 0 when y equals to 0. What does it mean? Y 0 at equilibrium, isn't it? So at equilibrium, acceleration equals to 0. When y equals to amplitude, or the object located at the amplitude, what happened to a? So a is maximum. So this is the way. How do you prove that? A 0 at equilibrium, and then a is maximum at the amplitude. Alright, so don't forget, okay, how do we use these two equations, which is the velocity and the acceleration. Okay, we may show them, okay, that v equals to 0 at which position, also a, by using these two equations. Okay, so let's discuss about the energy that we have in our simple harmonic motion system. Okay, so energy in simple harmonic motion, what do we have now? The total mechanical energy of simple harmonic motion system consists of two of it, which is kinetic energy, which is K, also the potential energy, which is U. Without damping, or there is no loss of energy from a system, the total energy of the system still remain constant, or we are talking about the conservation of energy. Okay, so total of energy, which is U plus K, still constant, or total of E initial equals to total of E final. Okay, so the equation of kinetic energy is K equal to half mv squared. According to the derivation before, v in term of y is v equal to plus minus omega square root of a squared minus y squared. We just substitute this v into this equation, giving you k equal to half m omega square root of a squared minus y squared, and it's squared here. Alright, so by rearrange the equations, then you will get k equal to half m omega squared and then a squared minus y squared. So this is the equation of k. So based on this, when the object located at the amplitude y equals to a, isn't it? So a minus a giving you 0. So k equals to 0. See, at the amplitude k equals to 0 means that the velocity also equal to 0, because kinetic energy is half mv squared, isn't it? So when y equals to a, again at amplitude, k 0, so that v also equal to 0. Again, see, at the amplitude, the object needs to stop for a while to change its directions to be backward. That is why k and v equals to 0. Okay, at the origin or equilibrium, y equal to 0. When y equal to 0, k is maximum, because a squared minus 0 giving you maximum values, which is a, isn't it? So that k is maximum here. Alright, and then for the potential energy, as we know according to the Hooke's law, F equals to ky. Okay, negative represented direction. Okay, Fs is the restoring force. So, and we know that according to Newton's second law, F net equals to ma. So by combining these two equations, giving you ma equals to negative ky. So as we know, according to the definition of simple harmonic motion, a equals to negative omega squared y. Substitute into this equation, you will get this. Alright, and then we know that k equals to m omega squared before, so we just substitute into this equation, giving you u equal to half ky. Alright, so k is m omega squared. We just substitute into this equation, and then you will get u equation, which is half m omega squared y squared. So according to this equation, when the object located at the amplitude y equals to a, isn't it, which is maximum displacement, so that u also maximum. At the equilibrium, y equals to 0, so that u also equals to 0. So this is the way how do we prove that k and u, is it maximum or 0, based on its position, which is at the origin or amplitude. Alright, so remember, this is the energy of the equation of kinetic energy and potential energy. Alright, so total energy is k plus u. So remember, the mechanical energy here is k plus u, or u plus k, still same. So we just substitute the equation of k and u into this equation, giving you this. And lastly, what do we get now? Okay, half m omega squared y squared plus half m omega squared a squared plus half m omega minus half m omega squared y squared. So y and y cancelling each other, giving you half m omega squared a squared only, isn't it? So this is the total energy. Alright, so total energy again, m omega squared, giving you k. So half ka squared, or half m omega squared a squared. So this is the total energy. Okay, now let's continue by 9.2, subtopic 9.2, which is about the graph of simple harmonic motion. So what do we have now? Students should be able to discuss the following graph, which is displacement against time, velocity against time, acceleration against time, and energy against displacement graph. Okay, how was the graph? Okay, let me show you one by one. Okay, basically the general equation of displacement is y equal to a sine omega t. Okay, let me show you how do we get this graph actually. So basically we just start by purely sine equation. So by giving you y equals to a sine omega t, the graph is purely sine. Purely sine graph just be like this. So this is y against t. And then we know that v equals to dy over dt. So we need to differentiate y with respect to t, which is d over dt a sine omega t, isn't it? So again, A just a constant, take out first. And then we need to differentiate sine omega t with respect to t, giving you cos omega t. And then we need to differentiate omega t with respect to t, giving you omega, isn't it? So that A and omega just a constant, we just collect these values 2 first. So A omega cos omega t. So this is the equation of V. So the equation of V is purely cos positive. Okay, purely cos positive. So cos should start from the amplitude. So this is the graph of V against time. Oh, before that, for Y against t, the y-axis is not representing amplitude. And then for V against t graph, the y-axis is not representing A omega. This one, amplitude. Okay, A omega. And then from V, we need to find A. So A equals to dV over dt. We need to differentiate V with respect to t, which is d over dt A omega cos omega t. Alright, again, A omega just a constant, take out first, A omega. And then we need to differentiate cos omega t with respect to t, giving you negative sign. And negative sine omega t. And then we need to differentiate omega t with respect to t, giving you omega, giving you negative A omega omega, which is A omega squared, and then sine omega t. So the graph of A now is purely sine but negative. How is it? Purely sine negative, just be like this lah. This is the axis. Purely sine negative. Okay, so this is the sine graph, which is negative. Alright, A against t. So the amplitude now representing A omega squared. So A omega squared, A omega squared. So this is a graph, see? Starting by purely sine equation. So this is purely sine graph for y against t. And then we just differentiate y, you will get v in terms of cos, purely cos. So the graph is purely cos, and the y axis not representing A omega, and for the amplitude. And then for the second differentiation, giving you A acceleration. So the acceleration now is purely sine negative, okay, equation. So the graph is purely sine but negative. And then the y-axis now representing the amplitude, which is A omega squared, which is our A. The one is A max. Alright, so this is the graph. So based on that, according to the note, okay, what do we have? Alright, so this is the equation of displacement, which is in terms of purely sine. So the graph is purely sine. So now the gradient, sorry, the amplitude here representing A lah. Alright, and then for the velocity against time, the graph is purely, sorry, from the equation which is purely cos. So the graph also purely cos here, where the amplitude now representing A omega. So A omega is V max, okay, maximum velocity, because the y-axis now representing velocity. Alright, and then for the second differentiation, giving you the acceleration. So the acceleration getting now just in purely sine negative. So the graph is purely sine negative. And then the amplitude now representing maximum acceleration, which is A omega squared. A omega squared. Alright, so this is the graph of displacement against time, velocity against time, and acceleration against time. So remember, the y-axis now representing 3 different values. The maximum displacement for y against t, maximum velocity for v against t, and maximum acceleration for a against t. Okay, how about the graph of energy against displacement? Alright, so remember, at the equilibrium, v is maximum, isn't it? When v maximum, giving you maximum kinetic energy. When kinetic energy is maximum, what happened to u? U equals to 0. Okay, alright, at the amplitude, the object needs to stop for a while, isn't it, to change its directions to be backward. So when v0, automatically k equals to 0. When k0 happen to u is maximum. All right. So for this graph, okay, please check. K is maximum. So at origin, the maximum value is now representing K. And then here, K is 0, isn't it? So the blue curve now representing kinetic energy. Alright. At the origin of equilibrium, U is 0. And then at the amplitude, U is maximum, isn't it? So the brown curve here representing our U. So this is K graph and this is U graph. Okay. So that this is K and this is U graph. Alright. And then the black line here representing our total energy. And this is our total energy actually. So the total energy is half m omega squared. Let me check first. Half kx squared. Sorry. Let me change the color lah. And that one is half m omega squared a squared. That one is the total energy. E total. Okay. So what does it mean? Let's say at this position. At this position, what happened? Alright, so let me change the color first. Okay, the brown one representing U. So this is our U. And this is our K. The blue one representing our K. Okay, at this position, this is K. Okay, so K plus U giving you E total. The energy is conserved. Okay. Alright, so at this position, what happened? Alright, so this is K. Okay, where is U? Okay, so this is U. Again, U plus K giving you E total. See, the energy still conserved. At any position, the total energy still remain constant. Okay, what do we have now? Changes in type of K and U only lah. At this point, K is smaller than U. At this position, U is smaller than K. But the total energy is still the same, equals to E total. So this is the way how do we read the graph. Okay. Okay, for the last subtopic, which is 9.3, we are talking about the period of simple harmonic motion. So for this subtopic, students should be able to use expression for period of simple harmonic motion for two different cases, which is simple pendulum and single spring. Okay, so no more derivation here. We just use the equation directly. Okay, what is the equation of period for these two different systems, which is simple pendulum and single spring? Let's start by the first one, under simple pendulum oscillation. Okay, as we know, the pendulum bob just oscillating back and forth again and again and again. So according to this situation, the equation of period given as the equation is, okay, period equals to 2 pi square root of L over G. So what is L? L is the length of the string of the pendulum. And that one is L. G is our gravitational acceleration. Alright, so we just substitute into this equation that we may calculate the period. So what is period? The time taken for one complete oscillation, involving 4 quarters lah. First quarter, second quarter, third quarter, and fourth quarter. So that is the time taken for one complete oscillation. We call it as period. So the condition for this equation, so remember the angle now has to be small, normally less than 10 degrees. Why? To avoid any energy loss. Okay, because by having greater angle, normally we are talking about friction by air, isn't it? So the angle should be smaller lah, less than 10 degrees. And then the string has to be inelastic and light. The string should be inelastic. What does it mean? There is no changes in length. Okay, and then the mass can be ignored. It's very light lah, for the string. And then only the gravitational force and tension in the string acting on the simple pendulum. So seems like it must free from any external force. The force exerted on the system, just the gravitational force, also the tension on the string. That's all. Okay, no more other forces. Okay, so there is no external force exerted on the system. It must be enclosed system here. All right. Okay, so this is the equation of period for our simple pendulum oscillation. All right, and then for the before that, okay, according to this equation, as I told you before, T is period, L representing the length of the string used now, and G is our acceleration due to gravity. All right, and then for the second apparatus here, which is single spring, the equation of period is T equals to 2 pi square root of m over k. So what is m? M is the mass of the object used now in that system, and k is the spring constant. So what is the condition in using this equation? Okay, first, the elastic limit of the spring is not exceeded when the spring is being pulled. Remember, it must obey the Hooke's law, because when the elastic limit just exceed here, it doesn't obey the Hooke's law anymore. What does it mean? It will not return back to its original length or shape when the force just removed. Okay, remember, first. Second, the spring is light and obeys the Hooke's law again. The spring, the mass can be ignored and still obey the Hooke's law. Alright, and the third one, there is no air resistance and surface friction. Seems like the system is free of any external force, which is friction, also air resistance. So by having these three conditions, then we may use this equation. Alright, okay, so I think that's all for chapter 9, which is the simple harmonic motion. Later, try to answer the tutorial questions. Okay, I think you don't have any problem lah, because it's quite easy. And this is our favorite chapter. Okay, see you again. Thank you.